A star dies in silence long before the universe hears its rhythm. Deep inside its collapsing heart, atoms are crushed, electrons vanish into protons, and a city-sized remnant is born spinning with the weight of a sun. Then, from its tilted magnetic poles, narrow beams of radiation sweep the darkness like a clock made from catastrophe. This is how a neutron star becomes a pulsar, not by burning brighter, but by turning death into time. Thank you for spending part of your day, or night, here with this story. If this calm journey through space helps you slow down, please give the video a like, subscribe for more quiet science, and share it with someone who enjoys the mysteries of the universe. Also, where are you watching from, and what time is it there right now? Leave a comment below. It is always beautiful to see where these signals reach. Now, let us enter the life, death, and pulse of a neutron star. Before a neutron star can flash across the galaxy as a pulsar, it begins as something far more familiar, a star held in balance. Not a quiet star like the sun, but a heavier one, born with enough mass to live fast, burn fiercely, and reshape its own interior through pressure and heat. In the long calm of its main life, the star is a furnace arranged around a simple contest. Gravity pulls every layer inward, drawing gas toward the center with patient force. Nuclear fusion pushes outward, releasing energy from the core as light and heat. For as long as these two pressures answer each other, the star holds its shape. It does not remain still, because no star is truly still, but it remains stable enough to shine across space for millions of years, pouring radiation from a surface made bright by the work hidden inside. Deep below that surface, atomic nuclei are being changed. Hydrogen becomes helium. Later, as the central fuel is consumed and the core contracts, helium and heavier elements begin to take part in new reactions. In a massive star, this sequence continues farther than it can in smaller stars. The core becomes layered by the ashes of earlier burning, as if the star is building a record of its own life from the inside outward. Each stage is shorter than the one before it. The earliest fuel lasts longest. The later fuels vanish more quickly, because they must burn at higher temperatures and under more severe conditions. The star becomes a delicate structure of shells, each one carrying out a different kind of fusion, each one helping to hold off the weight above it for a little longer. Yet the end is already being prepared. The outward pressure that supports the star is not an infinite supply. It depends on fuel, and fuel can be spent. In the center, the reactions eventually produce elements that no longer give the star useful energy when they fuse. Iron is the crucial turning point. It sits near the bottom of the energy curve for ordinary stellar fusion, which means that fusing iron does not release the energy needed to resist gravity. It asks for energy instead. Once the core becomes dominated by iron and similar heavy nuclei, the star has built a center that cannot save it. The furnace has made a weight that it cannot lift. Around this core, the outer layers may still burn in shells, bright and immense, but the center has entered a different story. It is no longer a place where fusion can provide a lasting outward push. It is a burden held up by more fragile forms of pressure, including the resistance of particles being squeezed together. For a while, that resistance matters. Electrons packed into the core resist compression through the rules of quantum physics, not through heat in the ordinary sense. Matter has a deep unwillingness to place identical particles into the same exact state. This principle gives the exhausted core a temporary stiffness, a strange kind of support that comes not from flame, but from the structure of nature itself. But the mass above it continues to press downward. The star has not chosen collapse. It has simply run out of ways to negotiate with gravity. The outer layers are enormous. Their weight bears down on the center. The iron core grows as shell burning adds more material onto it, and the balance becomes increasingly unstable. There is a threshold beyond which electron pressure can no longer hold the core apart. The star has spent its life delaying this moment. Now the delay ends. Gravity begins to win not gradually, but catastrophically. The inner core starts to fall inward, and the change moves through the star with stunning speed. Matter that once formed a hot, dense, but recognizable plasma is driven into conditions almost impossible to reproduce anywhere else in the universe. The core shrinks, density rises, temperature climbs to billions of degrees. Atomic order is destroyed under pressure. Heavy nuclei are broken apart by energetic light into smaller pieces, taking away energy that might otherwise have helped resist the collapse. Electrons are forced into protons, forming neutrons and releasing neutrinos. The matter in the core is being rewritten. What had been the center of a star becomes a place where ordinary atoms lose their structure, where the familiar separation between electron cloud and nucleus becomes irrelevant. The star is entering the narrow passage that may lead to a neutron star. At the same time, the old motion of the star becomes more important. A massive star is not perfectly motionless. It rotates. Its core rotates with it, even if the outer layers move differently and slowly exchange angular momentum through magnetic fields and internal currents. As the core contracts, the rotation rate increases. The same principle can be seen whenever a spinning body pulls its mass closer to its center, but inside a collapsing star the effect becomes extreme. A core many thousands of kilometers across begins falling toward a size comparable to a city. The rotation that once seemed mild can become rapid, and the magnetic fields threaded through the plasma are compressed and intensified. Nothing about this is yet a pulsar. There is no regular beam sweeping past a distant world, no lighthouse rhythm crossing the dark, but the ingredients are being gathered. Dense matter, rapid rotation, magnetic structure, a collapsing core that is no longer supported by ordinary stellar burning. The transformation is not smooth or gentle. It is the failure of a balance that lasted through the visible life of the star. It is also the beginning of a different kind of balance, one based not on fusion, but on the resistance of nuclear matter itself. In the last moments before the collapse becomes irreversible, the star may appear from outside as a swollen, luminous giant, its surface far removed from the drama at its center. Light leaving the outer layers gives little warning of the exact instant when the core yields. The surface is too distant from the center, and information cannot cross the star instantly. Deep within, however, the change is decisive. Gravity pulls the core inward faster and faster. The densities approach those found in atomic nuclei, but now extended across a macroscopic object. This is the quiet terror of massive stellar death. The star does not merely cool or fade. Its central region falls into a new state of matter. It passes through a boundary where chemistry has no meaning, where atoms are no longer the units of the world, where the difference between a stellar furnace and a compact remnant is measured in fractions of a second. The surrounding shells still contain the star's former richness: oxygen, silicon, carbon, helium, and hydrogen arranged through the vast envelope. They are about to be struck from below by the consequences of the core's collapse. Yet in this first movement, the essential event is inward. The star that once turned mass into light now gathers its remaining strength around a center that cannot endure. Every layer adds pressure. Every deeper region becomes less familiar. The calm shine of the surface continues for a moment, while beneath it the architecture of ordinary matter is being undone. A heavy star exhausts the engine that supported it. Gravity, always present and always patient, finally becomes the leading force. The iron center can no longer provide energy through fusion. Quantum pressure offers resistance, then fails under the growing mass. Particles are crowded into reactions that change the identity of matter. The core gives up its old form and begins to become something smaller, denser, and more extreme than any ordinary star. In that loss of balance lies the first step toward a pulsar. Though the pulses themselves are still hidden in the future, the eventual rhythm begins here, not with flashes, but with silence inside a dying star. As the centre folds inward and the universe prepares one of its most precise clocks from the ruins of a sun, the collapse of a massive star's core is not simply a fall inward, it is a change in what matter is allowed to be. In ordinary stars, atoms can be stripped of their electrons by heat and turned into plasma, yet the basic pieces remain recognizable. Electrons move freely. Atomic nuclei keep their identity. Pressure comes from heat, radiation, and the motion of particles. In the dying core of a massive star, those familiar supports are overwhelmed. Gravity presses inward with such force that the space between particles becomes a luxury the core can no longer afford. Electrons, which once helped provide a quantum stiffness against compression, are pushed into the very nuclei they had surrounded. There, they encounter protons, and the two are driven together. A proton and an electron can become a neutron, releasing a neutrino in the process. This reaction is called electron capture, but the name is gentler than the event. Across the collapsing core, countless protons are being transformed. Matter is losing its electrical balance in the old atomic sense and becoming more neutron-rich with every instant. The neutrinos produced in these reactions are almost ghost-like particles, able to pass through ordinary matter with extraordinary ease. Under normal circumstances, they would escape nearly unimpeded, carrying energy away from the star. But in the heart of the collapse, even neutrinos begin to feel the scale of the density around them. The core is becoming so compact that matter grows opaque even to particles that usually cross planets and stars as if they were mist. At first, many neutrinos stream outward. Later, as density rises, they become partly trapped, scattering through the deep interior and helping shape the violent event that follows. The core, meanwhile, continues inward. Its heavy nuclei are not merely squeezed closer together. Energetic photons break some of them apart, undoing the nuclear structures that earlier stages of stellar burning had built. This breaking apart consumes energy, which makes the collapse even harder to resist. The star is caught in a downward spiral. Pressure falls where pressure is needed most. Gravity accelerates the inward motion. Material that once occupied a vast central region rushes toward a shrinking center. Yet the collapse cannot continue in exactly the same way forever. As more matter becomes neutron-rich, the core approaches densities comparable to those inside atomic nuclei. At these densities, neutrons are packed so closely that the rules of quantum physics become a dominant source of resistance. Neutrons, like electrons, cannot all occupy the same quantum state. Their collective resistance forms a pressure that does not depend on ordinary heat. This is one reason a neutron star can exist at all. It is not held up by fire. It is held up by the behavior of matter when particles are forced into an almost unimaginable crowd. Near the center, the infalling material begins to encounter this new stiffness. The inner core, having fallen inward at enormous speed, decelerates sharply as nuclear density is reached. It becomes harder to compress, not because gravity is weakened, but because matter has entered a regime where further compression meets fierce resistance. The collapse halts in the innermost region, and the core rebounds. This rebound is not like a solid ball bouncing from a floor, because the star is not a simple object and its matter is not ordinary. It is a sudden change in motion, a shock born from the collision between continuing infall and a center that has become dramatically harder to squeeze. Around the inner core, Outer core material is still falling inward. It crashes into the stiffened center, and a shockwave forms at the boundary. For a moment, this shock begins to move outward, carrying the possibility of explosion, but the situation remains delicate. The shock loses energy as it travels through dense and falling material. It spends energy breaking apart heavy nuclei. Neutrinos stream and scatter through the region, carrying energy outward from the forming neutron star. Modern understanding of supernovae shows that the shock often needs help from neutrino heating and turbulent motion to become powerful enough to unbind the star's outer layers. The transition from collapse to explosion is therefore not a single clean bounce, but an intricate exchange among gravity, nuclear matter, neutrinos, magnetic fields, rotation, and fluid instabilities. In the center of it all, the remnant is taking shape. The object that will become a neutron star is forming from matter that has passed through the destruction of atoms and the merging of particles. Its composition is dominated by neutrons, although it is not made only of neutrons in a simple way. Protons, electrons, nuclei, and perhaps more exotic forms of matter may remain in different regions, depending on depth and pressure. But the defining transformation has occurred. The core is no longer an ordinary stellar core. It is a compact remnant being born under conditions where every familiar measure of density has failed. The release of neutrinos is vast. They carry away most of the gravitational energy liberated by the collapse. Light from the supernova may later become spectacular, but the greater flood is invisible to human eyes. Neutrinos leave the newborn remnant in immense numbers, bearing witness to the moment when a star's core became nuclear matter on a stellar scale. Their escape also helps cool the remnant and influences the surrounding material. They are not decorative byproducts. They are one of the central channels through which the collapse gives away its energy. The new neutron-rich core is extremely hot, but heat alone is not what defines it. Its deeper identity lies in density, gravity, and quantum resistance. Every small volume contains a staggering amount of mass. Matter is crushed until the old architecture of atoms is gone. The pressure is so high that the distinction between separate nuclei fades in deeper layers. This is the beginning of a world where the surface, crust, and core will later settle into strange arrangements. But during the collapse, those layers have not yet become calm. The newborn remnant rings with motion. It vibrates, convects, and adjusts under the burden of its own gravity. It may receive a kick from asymmetries in the explosion, sending it through space at high speed. It may inherit rapid rotation from the collapsing core. It may amplify magnetic fields through compression and internal motion. These inherited traits will matter later, because a pulsar requires more than a neutron star. It requires rotation, magnetism, and a geometry capable of sending regular beams across space. But at this stage, the most important change is deeper and more basic. Matter has crossed a threshold. The star has made neutrons not in a quiet laboratory, but in a gravitational catastrophe. The process is brief compared with the life of the star, yet it determines the nature of the remnant for ages to come. In a few moments, the core moves from being a burning center inside a massive star to being a compact object with its own strange physics. The surrounding star has not yet fully responded. The outer layers may still be falling inward or beginning to be driven away, depending on the exact moment in the event. The surface of the old star is far from the center, unaware in any immediate visual sense of the transformation below. But the core has already made its decision. It cannot return to ordinary stellar burning. It cannot spread back into a normal star. It has become too dense, too neutron-rich, too deeply bound by gravity. The formation of neutrons has removed much of the electron pressure that once opposed collapse, but the packed neutrons have created a new kind of support at a much smaller scale. This is the strange exchange at the heart of neutron star birth. One form of resistance fails, and another arises only after matter has been crushed almost to its limit. From this point forward, the remnant will be shaped by how much mass remains in the core. If the mass is too great, even neutron degeneracy pressure and nuclear forces may not be enough, and collapse may continue toward a black hole. But if the remnant mass lies within the range that nuclear matter can support, the collapse stops as a neutron star. It is not yet a pulsar in the observational sense. It is still wrapped in the violence of the dying star. Yet the core has become the object that can later pulse. Its matter has been transformed. Its neutrinos have poured outward, and its center has stiffened against gravity. The rhythm that may one day be heard by radio telescopes begins with this hidden conversion. When electrons and protons vanish into neutrons and the dying star's heart becomes something almost entirely new. The collapse has changed the star's heart, but the death of the star is not complete until the violence reaches outward. At the center, a compact neutron-rich remnant is forming, still hot, still settling, still flooded with neutrinos. Around it, the rest of the star is in motion. Layers that once burned in quiet shells are now falling inward or being struck by the shock born near the core. The old structure of the star, built over millions of years, is being erased in a matter of moments. The shockwave begins as the inner core stiffens and the surrounding material crashes into it. But its journey is difficult. It must travel through matter that is not empty space, not even thin gas, but dense stellar material plunging inward. As the shock pushes out, it loses energy by tearing heavy nuclei apart. It slows, weakens, and may stall. For the star to explode, the shock needs renewed strength, and much of that strength comes from the invisible flood leaving the newborn neutron star. Neutrinos pour through the region behind the stalled shock. Most pass on into space, but a small share deposit energy in the surrounding gas. In such an extreme event, even a small share of a vast energy reservoir can matter. Heated by neutrinos and stirred by turbulent motion, the material behind the shock becomes unstable. It boils and churns in huge rising plumes, carrying energy outward in an uneven flow. The explosion, therefore, is not a perfect sphere expanding with simple symmetry. It is messy, textured, and alive with instability. Some regions push outward more strongly than others. Some material falls back toward the remnant. Some is hurled into space. The core may receive a recoil from these asymmetries, a kick that sends the newborn neutron star moving through the galaxy like a dense ember released from a shattered furnace. This is the supernova threshold, the point at which collapse becomes a visible cosmic event. The inner transformation has made a compact remnant. The outer response makes the death of the star luminous. Once the shock gathers enough strength, it moves through the star's envelope and unbinds the outer layers. A vast mass of gas is launched into space, carrying the chemical products made during the star's life and during the explosion itself. Oxygen, carbon, silicon, iron group elements, and many other nuclei are mixed into the expanding debris. The star that once kept these materials hidden inside its layered body now releases them into the interstellar medium, where they may one day become part of new stars, planets, moons, dust grains, oceans, and living chemistry. A neutron star is born from the core, but the supernova is also a dispersal, a return of matter to the galaxy. The light of the explosion does not come directly from the first collapse alone. It develops as the shock reaches the outer layers and as radioactive isotopes made in the blast decay over time, warming the debris from within. To distant observers, the star may brighten dramatically, sometimes outshining entire regions of its host galaxy. Yet behind that brightness is a deeper imbalance being resolved. The old star cannot remain whole. Its core has become too compact, its envelope too violently disturbed, its internal supports gone. The explosion is the final separation between the remnant and the material that once surrounded it. At the centre, the neutron star may be left exposed only after the expanding debris thins enough for radiation to escape. In the earliest period, it is hidden inside the remnant of the supernova, wrapped in hot gas and dust moving outward at great speed. The object that may become a pulsar is already there, but its signal may not yet be visible. It is buried in its own birth cloud, rotating, cooling, and establishing the magnetic environment that will determine whether distant telescopes ever receive its pulses. Not every supernova leaves the same kind of remnant. If the core that remains is too massive, gravity may continue its work and pull the object into a black hole. The boundary depends on the mass of the remnant and the uncertain behavior of matter at extreme density. But when the remaining core is light enough to be supported by neutron degeneracy pressure and nuclear forces, a neutron star survives. Its survival is a narrow achievement. It is more compact than any ordinary star, yet not compact enough to vanish behind an event horizon. It is suspended between two gravitational futures, held at the edge by the strange pressure of dense matter. The supernova debris around it becomes a glowing record of the event. Filaments and clouds expand into space, shaped by the explosion, by surrounding gas, and by magnetic fields. Some remnants remain visible for thousands of years as delicate structures spread across light years. Within them, a pulsar may sit near the center, sometimes surrounded by a wind of particles accelerated by its rotation and magnetism. In such cases, the remnant is not merely an abandoned shell. It continues to be energized by the compact object inside. The neutron star loses rotational energy, and that energy can feed a nebula, making the space around it shine. But before that later phase, the essential act is separation. The supernova clears away the envelope that would otherwise hide the core forever. It strips the remnant down to the compact object left by collapse. This clearing is one reason a neutron star can become an observable pulsar. Without the explosion, the beams that may later form would be buried under too much stellar matter. The death of the star creates both the remnant and the open space around it. In this sense, a pulsar is not only the product of a dense core, it is also the product of an envelope being removed. The lighthouse needs a tower, but it also needs a horizon. The supernova gives the neutron star that horizon by casting the outer star away. In the expanding debris, the original star's history is scattered. The hydrogen envelope, if it still had one, races outward. Deeper layers follow, mixed and distorted by the blast. The clean onion-like arrangement of burning shells is broken into knots, clumps, and streams. The star's internal boundaries become outward-moving features in a growing cloud. For astronomers, these remnants are not just beautiful aftermaths, they are evidence. Their shapes, compositions, and motions contain clues about the explosion, the progenitor star, and the compact object left behind. Some remnants show signs of asymmetry, supporting the idea that the explosion was uneven. Some contain rapidly moving neutron stars displaced from the center, suggesting a powerful birth kick. Some reveal heavy elements forged or exposed in the final event. The supernova is therefore both an ending and a document. It records the conditions under which the neutron star was born. At the same time, the newborn remnant is undergoing its own early evolution. It is extremely hot, with a surface temperature far beyond that of normal stars. It cools first by neutrino emission from its interior, then later by light from its surface. Its crust forms as the outer layers settle into solid arrangements under enormous gravity. Its magnetic field, compressed and perhaps amplified during collapse, threads through the star and the surrounding plasma. Its rotation may be fast, though the exact rate depends on the angular momentum of the original core and the details of the explosion. These features do not become observationally important all at once. They mature into the conditions that define a pulsar. The supernova threshold is therefore not simply the moment a star explodes. It is the passage from hidden collapse to exposed remnant, from inward disaster to outward signal. The star's outer layers are thrown into the galaxy, and the neutron-rich core remains behind as a separate object. The violence that destroys the star also reveals the compact survivor. In the quiet that follows the first brightness, a new kind of object occupies the center of the expanding cloud. It is small compared with the star that made it, yet it carries much of the drama of that star's final seconds. It is dense enough to bend space-time strongly, hot enough to glow, magnetic enough to command charged particles, and perhaps rotating fast enough to make time itself seem audible through pulses. The supernova has not yet made a pulsar in the full sense. It has made the stage on which one can appear. It has cleared the remnant from its envelope, set the newborn neutron star adrift, and released the old star's matter into space. From this threshold onward, the story turns inward again, toward the city-sized object left at the center, where gravity, heat, density, and rotation are gathered into one of the most extreme bodies the universe allows. The object left behind by the supernova is small only in size. In every other sense, it is enormous. A neutron star may be no wider than a large city, yet it can contain more mass than the Sun. The contrast is so severe that familiar comparisons almost fail before they begin. Matter that once filled a brilliant stellar core has been compressed into a sphere only a few dozen kilometers across. The remnant is not a planet, not a normal star, and not a black hole. It occupies a narrow realm between ordinary matter and gravitational disappearance, held apart from further collapse by forces that only become decisive when particles are pressed nearly as close as nature allows. If a piece of it could be lifted away, which no ordinary process could do gently, even a small fragment would contain an immense mass. The star's gravity is correspondingly extreme. At its surface, falling matter would strike with energies far beyond anything experienced around ordinary stars or planets. A mountain could not stand tall there in the normal sense, because gravity would flatten almost any rise. The surface, if imagined as a crust of solid material beneath a thin atmosphere, would be astonishingly smooth by human standards, not because it is simple, but because weight is merciless. The remnant's gravity does more than pull matter downward, it bends the path of light. Photons leaving the surface climb out of a deep gravitational well, losing energy as they escape, shifting toward longer wavelengths. Light emitted from the far side can be curved around the star, so that more than a simple hemisphere may be visible from a distance. The neutron star distorts its own appearance by bending space-time around itself. It is not a black hole, because light can still escape, but it is compact enough for relativity to become part of its ordinary face. This is one reason neutron stars are valuable to physics. They are not abstract tests placed on paper. They are natural laboratories where gravity is strong, matter is dense, and light itself must follow curved geometry. The newborn remnant is also extremely hot. Its early temperature is far higher than the surface temperature of ordinary stars, although much of its first cooling happens through neutrinos escaping from the interior rather than through visible light alone. Over time, as the supernova debris expands and thins, the neutron star continues to radiate, cool, and settle. Its surface may glow in X-rays, especially when young, but the heat is only one layer of its identity. A neutron star is defined most deeply by density. Its gravity has compressed matter until atoms cannot exist as they do elsewhere. Near the outermost regions, there may be a thin atmosphere, perhaps made of hydrogen, helium, carbon, or heavier elements depending on the star's history and surroundings. Beneath that atmosphere lies a crust where nuclei and electrons are packed into a solid lattice. This crust is not like rock on Earth, though the word crust suggests hardness. It is a layer of nuclear material under pressures so high that the properties of solids become extraordinary. Deeper down, electrons are forced into nuclei, producing more neutrons. Nuclei grow more neutron-rich and more unstable by ordinary standards, but the pressure stabilizes configurations that could not survive in a laboratory. Farther still, the distinction between individual nuclei begins to blur. Matter may arrange itself into strange shapes under the competing influence of nuclear attraction, electric repulsion, and immense compression. These shapes have been nicknamed nuclear pasta, because theory suggests forms that resemble droplets, rods, slabs, tubes, and bubbles. The name is playful, but the material is not gentle. It may be among the strongest substances in the universe, able to resist deformation under conditions that would destroy ordinary matter completely. This layer is a bridge between the crust and the deeper core, where the behavior of matter becomes even less certain. In the core, densities rise beyond those of atomic nuclei, and the question of what matter becomes is still open. It may be mostly a fluid of neutrons with a smaller share of protons and electrons. Some of it may behave as a superfluid, a state in which matter flows without ordinary viscosity. Protons in some regions may become superconducting, allowing magnetic fields to interact with the interior in unusual ways. At still greater depths, some models suggest the appearance of exotic particles, or even matter in which quarks are no longer confined into separate neutrons and protons. These possibilities remain difficult to confirm because no instrument can peer directly into a neutron star's center. The star's interior must be inferred from mass, radius, cooling behavior, gravitational waves, bursts, and the timing of pulses. The city-sized remnant is therefore both an object and a question. It exists in the sky, but its inner structure remains partly hidden behind the limits of current theory. The surface gravity also creates a strange relationship with time. Clocks near the surface would run more slowly compared with clocks far away, not because of mechanical failure, but because gravity changes the passage of time itself. The effect is not a fantasy layered onto the object, it is a prediction of general relativity. And neutron stars live where such predictions matter. Radiation leaving the surface carries the imprint of this gravitational environment. Matter orbiting nearby must move at tremendous speeds. Any loose material falling in from a companion star or from surrounding debris can be heated to extreme temperatures, releasing X-rays as it spirals inward. A neutron star in isolation may be hard to see, but a neutron star interacting with matter can become brilliant. Still, the route to becoming a pulsar depends most directly on two inherited properties, rotation and magnetism. The remnant is compact, and because it was formed from a collapsing core, it often spins rapidly. The more the core shrank, the faster its rotation could become, depending on how angular momentum was redistributed before and during the explosion. A neutron star can rotate in fractions of a second, and some rotate hundreds of times each second. The surface, bound by extraordinary gravity, moves through a regime where the scale of the object makes rapid rotation possible without immediate breakup. This rotation stores energy. A pulsar is, in many cases, a rotating neutron star gradually spending that energy through electromagnetic radiation, particle winds, and sometimes gravitational effects. But the rotation alone is not enough. A smooth, hot, rapidly spinning sphere with no strong magnetic structure would not send out the same sharply timed beams. The neutron star also carries a magnetic field inherited and intensified during collapse. Field lines that once threaded a large stellar core are squeezed into a far smaller volume. The result can be a magnetic field immensely stronger than those familiar on planets, strong enough to control the motion of charged particles in the surrounding space. In some neutron stars, the field is stronger still, producing magnetars, objects whose magnetic energy can power violent X-ray and gamma-ray activity. For an ordinary pulsar, the field need not reach magneta extremes, but it must be powerful enough to shape a magnetosphere. This magnetosphere is the region around the star where charged particles are forced to follow magnetic field lines, and where rotation twists the electromagnetic environment into a dynamic structure. The city-sized remnant therefore becomes more than a dense sphere. It becomes a rotating magnetic engine. Its gravity holds it together. Its interior stores mysteries of nuclear matter. Its crust may crack or adjust as the star spins down. Its magnetic field reaches outward into space. Its rotation provides a regular clock. But at this stage in the story, the remnant is not automatically a pulsar visible from Earth. Many neutron stars may never reveal themselves as pulsars to any particular observer, because their beams do not sweep in the right direction, or because their emission weakens, or because the geometry is unfavorable. The neutron star must develop an ordered pattern of particle acceleration and radiation, and that pattern must cross a line of sight. Still, the essential body now exists. The supernova has removed the envelope. The core has become dense enough to survive as a neutron star. The remnant has emerged as a compact object where gravity, heat, rotation, and magnetism are bound together. It is a quiet-looking point from far away, perhaps invisible at first through the debris of its own birth. Yet it contains a world of extremes. Across a few dozen kilometers, it gathers the mass of a star, the curvature of strong gravity, the pressure of nuclear matter, and the stored motion of a collapsing core. The path toward a pulsar will now depend on how this small remnant moves and how its magnetic field reaches outward. The old star has vanished into expanding gas. At the center remains the city-sized object, dense enough to challenge matter, bright enough to cool for ages, and structured enough to begin turning rotation into signal. A neutron star inherits its spin from a much larger star, but the inheritance is transformed by collapse. Before the supernova, the massive star already rotates, carrying angular momentum in its core and outer layers. Angular momentum is the measure of rotational motion, and in an isolated system it is difficult to simply erase. When the core falls inward, its matter moves closer to the rotation axis, and the spin rate rises. The principle is simple, though the setting is extreme. A broad, slowly turning core becomes a compact remnant, and the old motion is concentrated into a far smaller space. The same amount of rotational motion, confined within a city-sized sphere, can become astonishingly rapid. In this way, the neutron star is not spun up by some later external motor at first. It is born from collapse already carrying the memory of the star's rotation, compressed into a denser and faster form. The exact speed depends on the history of the original star. Some massive stars lose angular momentum through winds before they die. Some exchange it with a companion in a binary system. Some have internal magnetic fields that help move rotational energy from the core to the outer layers. For this reason, not every neutron star is born spinning at the same rate. Yet even a modestly rotating stellar core can produce a compact object whose rotation is far faster than anything familiar among ordinary stars. What had once taken days or longer may become a turn completed in seconds, fractions of a second, or less. The newborn neutron star becomes a rotating relic, a dense survivor carrying forward one of the most basic motions of the body that made it. This rotation matters because it provides an energy reservoir. A neutron star may be hot when it forms, and it may possess a powerful magnetic field, but the steady rhythm of a pulsar is tied to spin. The star turns again and again with extraordinary regularity. Its crust and magnetic environment rotate with it, and if radiation beams form near the magnetic poles, those beams sweep through space at the same rate. The pulse is therefore not usually a star brightening and dimming over its whole surface. It is a rotating geometry. The star is more like a compact clock whose visible signal depends on direction. When the beam points across a distant telescope, the pulsar appears to flash. When the beam points elsewhere, the same neutron star may pass unnoticed. The spin gives the pattern its timing, and the compactness gives the timing its precision. A normal star is vast, fluid, and turbulent, with a surface spread across immense distances. A neutron star is small and tightly bound, so its rotation can remain stable over long stretches of time. This stability is why pulsars became famous as cosmic clocks. Their pulses can arrive with such regularity that tiny changes become meaningful. Astronomers can measure the gradual slowing of the spin, the influence of a companion star, the motion of the pulsar through space, and even subtle effects predicted by relativity. Yet this precision is not absolute stillness. The neutron star is losing energy. Its rotating magnetic field and particle wind carry energy away. As energy leaves, the star's rotation slows. The effect may be tiny from one rotation to the next, but over thousands, millions, or longer spans, it changes the pulsar's period. The star spins down. This slow loss of rotational energy is one of the main ways ordinary pulsars age. A young pulsar may rotate quickly and power a bright nebula around it. An older one may rotate more slowly, with weaker emission, until it may eventually cross a threshold where the pulsar mechanism fades. Rotation also shapes the body of the neutron star itself. A rapidly spinning object is slightly flattened, wider around its equator than from pole to pole. In a neutron star, the effect is constrained by overwhelming gravity, but it is still part of the star's structure. As the star gradually slows, the preferred shape changes. The crust, which is formed under enormous pressure, must adjust to the weakening centrifugal effect. Sometimes it may not adjust smoothly. Stress builds. A tiny fracture or rearrangement can occur, often described as a starquake, because the object is so dense and compact. Even a small internal shift can alter the moment of inertia, the way mass is distributed relative to the rotation axis. If the moment of inertia changes, the spin can briefly change as well. Observers see this as a glitch, a sudden small increase in rotation rate followed by a gradual recovery. Such glitches reveal that the neutron star is not a perfectly rigid clock. It is a layered physical object with a crust, interior fluids, and perhaps superfluid components that exchange angular momentum in subtle ways. The spinning relic therefore teaches two lessons at once. It is stable enough to keep time across the galaxy, yet complex enough to show the hidden motions of matter inside. The role of superfluidity may be especially important. In parts of the neutron star interior, neutrons may form a superfluid, a state of matter that can move with almost no ordinary friction. A superfluid inside a rotating star does not simply swirl like water in a bowl. It organizes rotation into many tiny vortices, each carrying a small share of angular momentum. These vortices may interact with the crust. They may become pinned, held in place by the structure of dense matter, while the outer crust slowly spins down under magnetic braking. Over time, a difference can build between the rotation of the crust and the rotation of the interior superfluid. When vortices suddenly unpin and move, angular momentum can be transferred outward, producing a glitch. This is one way the pulse timing of a distant star becomes a messenger from matter hidden far beneath the surface. The regular beat is interrupted by a minute adjustment, and that adjustment carries clues about nuclear physics under pressures that cannot be recreated on Earth. But the rotation has another purpose in the making of a pulsar. It animates the magnetic field. A stationary magnetic neutron star would still be extreme, but a rotating magnetized neutron star creates a changing electromagnetic environment. The magnetic field lines are carried around by the star, and the surrounding charged particles respond. Near the star, the magnetosphere may rotate with it, locked into the motion of the magnetic field. Farther out, there comes a boundary where co-rotation would require particles to move at the speed of light. This boundary is called the light cylinder, not because it is a solid surface, but because it marks a limit in the rotating geometry. Beyond it, magnetic field lines cannot remain closed and smoothly co-rotating in the same way. Some open outward, allowing particles and electromagnetic energy to escape. The faster the star spins, the more compact and energetic this structure can be. Rotation turns the magnetic field into an engine, and the engine can power radiation beams. The star's spin, therefore, is not merely a timing device after the pulsar exists. It helps create the conditions for the pulsar to exist. It drives electric fields, accelerates charged particles, and supplies the energy that emerges as radio waves, X-rays, gamma rays, or a wind of relativistic particles. A pulsar is often described through its beam, but beneath the beam is the rotation of the neutron star spending itself. Each pulse is a tiny withdrawal from the stored rotational energy left by collapse. The star slows by almost immeasurable amounts, yet the accounting continues. Over time, the period lengthens, the signal changes. The pulsar moves through its life as a rotating remnant, gradually giving its birth motion back to space. Some neutron stars gain spin later. In binary systems, a neutron star can pull matter from a companion. As material spirals in, it carries angular momentum, and some of that angular momentum can be transferred to the neutron star. This process can recycle an old neutron star, spinning it up until it rotates hundreds of times each second. Such millisecond pulsars are among the most stable rotators known, ancient objects made fast again by companionship. They show that pulsar rotation is not always only a memory of birth, it can also be renewed by long interaction. Still, the first path from neutron star to pulsar begins with collapse, with the contraction of a stellar core into a compact remnant that spins far faster than its parent ever did. The rotating relic now stands at the center of the story. It is dense enough to hold itself together against immense centrifugal forces, structured enough to store and release angular momentum, and magnetic enough for its spin to matter beyond its surface. Without rotation, the neutron star would remain extreme but quiet in a different way. With rotation, it becomes capable of rhythm. The next step lies beneath and around that spinning surface, in the hidden interior, and the strange forms of matter that allow the star to behave as both an almost perfect clock and an unsettled physical world. Inside a neutron star, the making of a pulsar becomes more than a story of rotation and magnetism. It becomes a story of matter pressed into forms that have no ordinary counterpart. From a distance, the star may seem like a simple point, a compact remnant turning in space, but its interior is layered, strained, and partly unknown. The surface is the least mysterious part, and even there the word surface must be used carefully. A neutron star may possess a very thin atmosphere, perhaps only a shallow skin of light elements or heavier atoms, depending on what has fallen onto it and what the supernova left behind. Beneath this atmosphere lies a solid crust, not rock, not metal in the everyday sense, but a lattice of atomic nuclei and electrons shaped by gravity so intense that the smallest irregularity is pressed flat. The crust is only a small fraction of the star, yet it matters greatly. It anchors magnetic fields, carries stresses, and may crack or shift as the star ages. When the neutron star spins down, the crust is asked to change shape, and if it resists too long, a sudden adjustment can travel through the star as a tiny quake. To an observer far away, that hidden fracture may reveal itself as a glitch in the pulse timing, a small and abrupt change in the rotation of the visible clock. Deeper in the crust, the nuclei become more exotic. The pressure rises, and ordinary nuclear stability gives way to arrangements that cannot exist freely in a laboratory. Electrons are squeezed into protons, increasing the number of neutrons inside nuclei. These neutron-rich nuclei grow heavier and stranger, held together by pressure that prevents them from immediately falling apart. Eventually, neutrons begin to drip out of nuclei, forming a sea of free neutrons around the remaining nuclear clusters. This neutron drip region is one of the first signs that the star is no longer behaving like matter elsewhere in the cosmos. The familiar distinction between a nucleus and its surroundings becomes less clean. Particles are so densely packed that each layer prepares the next loss of ordinary structure. Still deeper, the competition among forces becomes delicate. The strong nuclear force pulls nearby nucleons together. Electromagnetic repulsion pushes charged protons apart. Gravity demands compression. Under this competition, matter may arrange itself into long rods, flat sheets, tunnels, and bubbles. These predicted structures are known as nuclear pasta, a name that sounds domestic only because the shapes need some human language. In reality, this material may be extraordinarily strong, perhaps one of the strongest forms of matter in the universe. It may influence how the crust breaks, how heat moves, and how magnetic stresses are stored. Within a pulsar, such hidden structures are not decorative details. They are part of the machinery that determines how smoothly the star turns, how its magnetic field evolves, and how the signal may change over time. Below the crust lies the outer core, where most of the matter is likely a dense fluid of neutrons, with smaller populations of protons, electrons, and perhaps other particles. The word fluid might suggest softness, but this is a fluid only in the language of physics. It is denser than atomic nuclei and bound under immense gravity. The neutrons may form a superfluid, a phase in which matter flows without ordinary viscosity. Superfluidity changes the interior from a simple spinning mass into a more subtle rotating system. A superfluid cannot rotate exactly like a solid body. Its rotation is carried by quantized vortices, tiny threads of circulation that together imitate the star's larger spin. These vortices can become pinned to structures in the crust or interact with other components inside the star. As the outer crust gradually loses rotational energy through the pulsar mechanism, parts of the superfluid may lag behind or maintain their motion. Tension builds between layers that are coupled imperfectly. When that tension is suddenly released, angular momentum can move from the interior to the crust, and the observed spin can jump. A distant telescope sees a glitch. The star itself has merely shifted some of its hidden motion from one reservoir to another. In this way, pulse timing becomes a probe of an interior that cannot be seen. The repeated flash of a pulsar is a surface and magnetospheric event, but its tiny irregularities carry messages from deep matter. The protons in the core may also enter a superconducting state, where electrical currents and magnetic fields behave in ways unlike those in normal plasma. If superconductivity exists there, the magnetic field may be confined into thin tubes of magnetic flux, interacting with neutron vortices and slowly evolving over long spans of time. This is important because a pulsar is not only a rotating object, it is a rotating magnetic object. The magnetic field seen outside the star may be anchored, twisted, or rearranged by processes inside. If the interior is superconducting, then the star's magnetic history may be written not only in the magnetosphere, but in the deep coupling between charged particles and superfluid neutrons. The field that helps create beams in space may be connected to structures buried under layers of nuclear matter. This connection remains difficult to describe fully, because the physics lies at the boundary of nuclear theory, condensed matter, physics, and relativity. A neutron star is small enough to seem simple, but its simplicity is deceptive. It forces many branches of physics into one object. At greater depths, the uncertainty grows. The central core may contain matter at densities beyond those of ordinary atomic nuclei. Scientists do not yet know exactly what happens there. It may remain mostly neutrons and a smaller mixture of other particles, or heavier particles may appear, such as hyperons, which contain strange quarks. Another possibility is that neutrons and protons lose their individual identities under pressure, allowing quarks to move through a larger region as deconfined quark matter. In some models, the innermost core could contain a color superconducting phase, a state whose name comes from the quantum properties of quarks rather than any ordinary color. These ideas are not fantasy, but they are uncertain. They arise from efforts to extend known physics into a realm where direct experiments are limited and observations must be interpreted carefully. The core of a neutron star is therefore a scientific frontier hidden inside an astronomical object. It is a place where known matter may remain known, or may become something partly new. This uncertainty affects the whole star. The exact behavior of dense matter determines how massive a neutron star can be before becoming a black hole. It shapes the relation between mass and radius. It influences how the star cools, how it deforms, and how it responds during collisions with other neutron stars. Pulsars help constrain these possibilities because their timing can reveal masses. Their radiation can suggest surface temperatures, and their behavior over time can hint at interior processes. Some pulsars in binary systems allow especially precise mass measurements, and the existence of relatively heavy neutron stars shows that dense matter must be stiff enough to support them. Gravitational waves from neutron star mergers add another kind of evidence, revealing how easily these objects deform under tidal forces before they collide. Each measurement is indirect, but together they narrow the range of possible interiors. Yet there is a gentle irony in the pulsar's nature. The signal that reaches Earth may be simple, a pulse arriving again and again, separated by an almost steady interval. Behind that simplicity lies an interior of extraordinary complexity. The beam sweeps space because of magnetospheric physics, but the stability of the sweeping depends on the compact body beneath. The crust must hold its shape. The superfluid must exchange angular momentum in subtle ways. The magnetic field must remain organized enough to feed particle acceleration. The dense core must support the star against collapse. A pulsar is therefore not merely a lighthouse attached to a sphere. It is the visible rhythm of a layered object in which matter has been pushed to the edge of its possible forms. Every pulse depends on the survival of that arrangement. If the mass were greater, the star might have become a black hole, removing the surface and the lighthouse altogether. If the magnetic field were weaker, or the rotation too slow, the beams might fade. If the interior couples differently, the timing may drift, glitch, or recover in another pattern. The hidden interior gives the pulsar both its steadiness and its imperfections. It is the reason the object can behave like a clock, and also the reason the clock can reveal that it is alive with physics beneath the dial. From the outside, the next step toward the pulsar seems to be the emergence of magnetic beams. But before those beams can be understood, the star must be recognized as a dense, layered remnant whose interior is still partly unresolved. Its crust is a solid shell under impossible pressure. Its pasta layers may store strength in unfamiliar shapes. Its core may flow as a superfluid and conduct as a superconductor. Its deepest center may contain matter whose true nature is still unknown. The pulse that eventually crosses a telescope is brief, clean, and regular. The body that creates it is anything but simple. In the hidden interior of the neutron star, the universe keeps one of its quietest mysteries, not in darkness alone, but in matter compressed so deeply that even the meaning of matter begins to change. The magnetic field of a neutron star is not added after the star is born. It is carried inward with the collapsing core, concentrated, distorted, and amplified as the stellar remnant shrinks into a volume far smaller than the body that once held it. A massive star already contains magnetic fields, woven through its plasma by motion, rotation, convection, and electrical currents. In the ordinary life of the star, those fields may be wide and diffuse, spread through a vast interior and outer envelope. When the core collapses, the same field is compressed into a much smaller region. Field lines are crowded together as matter falls inward, and the strength of the field can rise enormously. This is one of the quiet inheritances of stellar death. The star loses its bright outer layers, but it leaves behind a magnetic structure intensified by gravity. In a neutron star, that structure becomes powerful enough to shape the space around the remnant. It no longer acts as a minor influence hidden inside a larger star. It becomes one of the defining features of the object, reaching outward from the surface and forcing charged particles to move in ordered paths. The field is not visible by itself, but its effects are everywhere. It governs how plasma moves near the star. It helps determine where particles accelerate. It stores energy that can be released slowly, or in some neutron stars, suddenly and violently. It gives the compact remnant a direction, a set of poles, and eventually a way to turn rotation into beams. The strength of this magnetism is difficult to imagine, because everyday magnetic fields are gentle by comparison. On Earth, magnetic fields can guide compasses, confine laboratory plasma, or help medical instruments form images of the body. Around a neutron star, the field can be trillions of times stronger than the planet's natural field, and in magnetars it can become stronger still, at those intensities. Magnetism is not merely a force acting on charged particles. It becomes part of the physical character of the region around the star. Atoms near the surface may be stretched into elongated shapes. The motion of electrons is constrained so strongly that normal material behavior changes. Even empty space can respond through quantum effects, allowing light to behave as though it is passing through a strange medium. Such ideas arise from known physics pushed into rare conditions. For a pulsar, the important region is the magnetosphere, the volume surrounding the star where magnetic fields and charged particles interact. A neutron star does not sit in complete emptiness. It may be surrounded by plasma left from its birth, particles pulled from its surface, or matter created in intense electromagnetic processes. The rotating magnetic field sweeps through this plasma and organizes it. Charged particles cannot simply drift wherever they please. They spiral along magnetic field lines, moving more easily parallel to the field than across it. Near the star, the magnetic field is so strong that the particles are tied closely to its structure. In this way, The invisible field creates an architecture around the remnant, a kind of rotating magnetic atmosphere far larger than the solid star beneath it. This architecture is essential because a pulsar's light does not come only from a glowing surface. Much of the signal arises from charged particles being accelerated in the magnetosphere, where electric and magnetic fields combine in extreme ways. Rotation is the engine, but magnetism provides the wiring. As the neutron star spins, it drags its magnetic pattern around. If the magnetic field were perfectly simple and perfectly aligned with the rotation, the surrounding environment would still be energetic, but the pulse geometry would be less favourable. In most pulsars, the magnetic axis is tilted relative to the rotation axis. Before that, tilted geometry can produce the lighthouse effect. However, the field must be strong enough to command the plasma. It must carve the region into zones of closed and open field lines. Closed field lines loop back to the star, trapping charged particles near the remnant. Open field lines extend outward into space, giving particles a path to escape. Along these open regions, acceleration can become especially important. Particles can be driven to nearly the speed of light, releasing radiation as they move through curved magnetic fields and interact with surrounding photons and fields. The details are complex and still studied, but the larger idea is clear. A neutron star becomes a pulsar when its rotating magnetosphere can channel energy outward in a repeating pattern. The magnetic field also acts as a brake. A rotating magnetized neutron star loses energy because its field and particle wind carry energy away into space. This loss gradually slows the star's spin. Each pulse is connected to a tiny decrease in the star's rotational energy. The field draws from the spinning remnant and exports that energy as radiation and particles. Over long periods, the star's period lengthens. Its magnetic power may evolve. The pulsar moves through a life shaped by magnetic braking, first energetic and fast, then slower and quieter, unless a companion star later spins it up again. The same field that helps make the pulsar visible also helps age it. It is both the source of the beam structure and the mechanism through which the rotation is spent. Astronomers can observe how quickly the rotation period changes and use that slowdown to infer properties of the magnetic field and the pulsar's history. The field is not always calm in some neutron stars, especially those with exceptionally intense magnetic fields. The crust may be stressed by magnetic forces from within and without. As the field shifts or rearranges, it can strain the solid crust. If the crust cracks or the magnetosphere reconfigures, bursts of high-energy radiation may appear. Magnetars are the most dramatic examples, where magnetic energy itself becomes a central power source. Ordinary pulsars are usually steadier, driven mainly by rotation, but they still belong to the same broad family of magnetized neutron stars. Their behavior depends on how the field is anchored, how it evolves, and how it interacts with the star's interior. A pulsar is not only a spinning object with a beam, it is a magnetic body whose outer signal is tied to deep currents and hidden structures. The amplification of the magnetic field during collapse may come from more than simple compression. Rapid rotation and turbulence in the newborn neutron star can strengthen fields further through dynamo processes, where moving conductive fluid converts kinetic energy into magnetic energy. The early remnant is hot, convective, and violently adjusting. In such an environment, magnetic fields may be wound, twisted, and reinforced. Different birth conditions may help explain why some neutron stars emerge as ordinary radio pulsars, others as magnetars, and others as quieter objects detected mainly by their heat. The final magnetic field is a record of the collapse, but it is also a record of the star's internal motion during its first moments. Those moments are brief, yet they may determine the remnant's observable personality for thousands or millions of years. A stronger field can drain rotational energy more quickly. A weaker field may allow a neutron star to remain less conspicuous. A tilted field can make pulses visible from certain directions, while a different orientation may hide the signal from Earth. The magnetic field therefore introduces a kind of cosmic selectivity. Many neutron stars may exist without appearing as pulsars to a given observer. Their beams may miss the line of sight, their magnetospheres may be too weak, or their rotation may have slowed beyond the active range. The sky does not show all neutron stars equally. It shows those whose magnetic and rotational geometry happens to send radiation toward the instruments watching from afar. Behind every detected pulsar, there may be many compact remnants whose beams sweep elsewhere, or whose engines have faded into silence. Still, wherever a pulsar is seen, magnetism is central. It gives the star poles that need not match its spin. It channels particles into narrow regions. It helps generate the electromagnetic waves that escape into the galaxy. It controls the outflowing wind that can shape a nebula around a young pulsar. It reaches beyond the surface like an invisible skeleton, turning a dense sphere into a structured cosmic transmitter. The neutron star's mass and density make it possible. Its rotation gives it rhythm, but the magnetic field gives that rhythm a direction. Without it, the remnant might remain a compact cooling object. Fascinating, but much harder to hear across interstellar distance. With it, the star becomes capable of drawing lines through space, accelerating particles along them, and sending out radiation in a pattern that can cross a distant world again and again. This is where the path to a pulsar sharpens. The neutron star has already been born from collapse. It has already inherited rapid rotation. Its interior has become a layered realm of dense matter. Now its magnetic field intensifies and reaches outward, organizing the plasma around it into a magnetosphere. The invisible architecture is in place. The next transformation will depend on orientation. If the magnetic axis were the same as the rotation axis, the beams might not sweep broadly across the sky. But when the magnetic poles are tilted away from the spin, the rotating field becomes a moving signal. The amplified magnetism prepares the beam, and the star's spin prepares the rhythm. Together they bring the remnant closer to becoming a neutron star, but a pulsar, a compact object whose hidden magnetic order is made visible through time. A neutron star becomes a pulsar not simply because it spins, and not simply because it is magnetic. The crucial step is that these two properties usually do not point in the same direction. The star rotates around one axis, the invisible line through which its body turns. Its magnetic field has another axis, marked by the north and south magnetic poles where field lines emerge and return. In many neutron stars, these axes are tilted relative to each other. This misalignment is a quiet geometric fact, but it changes everything. A beam tied to the magnetic poles does not remain fixed in one direction as the star turns. It sweeps around the rotation axis, tracing a cone through space. If that cone crosses Earth, the neutron star appears to pulse. If it misses, the same object may remain hidden, or may be detected only by other signs. The difference between silence and rhythm can depend on a simple angle. This tilt is not surprising when the violence of formation is considered. The supernova is uneven. The collapsing core is turbulent. Rotation, convection, magnetic fields, and fallback material all interact in a brief and chaotic birth. There is no reason for the final magnetic field to settle perfectly along the spin axis. The magnetic structure may be inherited from the original star, twisted during collapse, strengthened by internal motion, and then locked into the crust and superconducting regions beneath it. The rotation axis reflects the total angular momentum of the remnant, These histories overlap, but they are not identical. The result is often an oblique rotator, a compact star whose magnetic poles are carried around like tilted lanterns on a turning body. The term sounds technical, yet it describes the heart of the lighthouse effect. A lighthouse is visible from far away, not because its lamp brightens and fades at random, but because a directed beam rotates across the horizon. A pulsar works in a related way, though its beam is born from plasma, magnetic fields, and relativistic particles rather than glass and machinery. The star may emit radiation continuously along regions near its magnetic poles, but a distant observer receives it only when the rotating geometry lines up. The pulse is therefore an encounter between the beam and a line of sight. It is not the whole star breathing in brightness. It is a narrow window opening and closing as the neutron star turns. This explains why pulsars can be so regular. The rhythm is anchored in rotation, one of the most stable properties a compact object can possess. But it also explains why many neutron stars are unseen as pulsars. Their beams may never sweep across Earth. The galaxy may be full of dense rotating remnants whose signals pass above, below, or beside every telescope. The observed population is only the portion whose geometry happens to include the line from the star to this planet. The magnetic axis does more than aim the beam. It shapes the surrounding magnetosphere. Near the magnetic poles, field lines can open outward, connecting the surface to distant space rather than looping back to the star. These open field regions become natural channels for charged particles, electrons and positrons, and in some settings, ions, can be pulled from the surface or created in cascades above it. The star's rotation generates electric fields that accelerate these particles to extreme energies. As they stream along curved magnetic field lines, they release radiation. Some of this radiation appears in radio wavelengths, some in higher energy bands, depending on the region where it is produced and the physical conditions there. The beam is therefore not a solid cone of light emerging from a lamp. It is a structured zone of emission created by particles moving through a rotating electromagnetic environment. Its shape may be hollow, patchy, layered, or changing with altitude. This complexity is why pulsar profiles differ. Some produce one clear pulse per rotation. Others produce a main pulse and an interpulse, suggesting that both magnetic poles may be visible, or that a wide beam crosses the line of sight in more than one way. Some show drifting subpulses, subtle changes in the radio emission from one rotation to the next. These variations are not random decoration. They reveal that the magnetosphere has its own plasma weather, its own patterns of acceleration and discharge, while still being tied to the underlying clock of the star's spin. The tilted magnetic axis also helps define the pulsar's energy loss. As the magnetized star rotates, it radiates electromagnetic energy and launches a wind of particles. An aligned rotator can still lose energy. Because plasma-filled magnetospheres are more complex than simple textbook vacuums, but the oblique geometry enhances the time-varying character of the field. The rotating tilted dipole acts like a powerful electromagnetic engine, sending energy outward. This energy must come from somewhere, and it comes mainly from the star's rotation. Over time, the pulses slowly separate as the spin period lengthens. The same misalignment that helps make the pulsar visible also participates in the gradual draining of its rotational reservoir. In some theories, the angle between the magnetic and rotation axes may itself evolve. The star may slowly move toward alignment, or in some cases toward greater separation, depending on the coupling between the crust, interior, magnetosphere, and energy loss processes. Such changes are hard to measure directly, but they matter because the pulsar beam is a geometric signal. A small change in angle can alter the pulse shape, the brightness, or whether the beam remains visible at all. A pulsar's life is not only a slowing clock, it may also be a slowly changing orientation. The birth tilt may decide whether the star is seen in its youth, while later evolution may decide how long the beam remains detectable from a given direction. The geometry is made even more subtle by relativity. Near the neutron star, gravity bends light, so radiation leaving the magnetic pole does not travel exactly as it would from a weak gravitational field. Light from regions that might otherwise be hidden can curve into view. This bending can broaden the range of visible emission and soften the simple picture of a narrow beam sweeping through empty space. At the same time, the rapid rotation affects how emission is received. Radiation from particles moving at nearly the speed of light is beamed strongly in the direction of motion. The exact pulse shape depends on where in the magnetosphere the emission is produced, how fast that region is moving, how the magnetic field curves, and how the beam crosses the observer's line of sight. A simple tilt creates the basic rhythm, but the detailed pulse profile is a map of motion, gravity, and magnetic structure. In young pulsars, the tilted geometry can feed a surrounding nebula. The rotating magnetic field drives a wind of energetic particles outward. When that wind strikes slower material in the supernova remnant, it can form a pulsar wind nebula, a glowing bubble powered by the neutron star's spin. The lighthouse beam and the broader wind are different expressions of the same engine. One sends timed flashes along particular directions. The other pours energy into the surrounding space more broadly. Both depend on the rotating magnetosphere, and the magnetosphere depends on the relation between spin and field. In this sense, the tilted magnetic axis gives the remnant a dynamic connection to the galaxy. It does not merely sit at the center of the supernova debris, it turns, accelerates particles, sheds energy, and sculpts its environment. The poles become outlets through which the star's hidden rotation is made visible. The tilt also carries a deeper observational lesson. When astronomers measure pulsars, they do not observe the neutron star from all sides. They receive whatever portion of the beam crosses their instruments. The pulse profile is like a narrow slice through a larger emission pattern. From that slice, they infer the geometry of the magnetic field, the angle of the spin axis, the width of the beam, and the altitude of the emission region. This makes pulsar astronomy both precise and indirect. The arrival times can be measured with extraordinary accuracy, yet the full shape of the magnetosphere must be reconstructed from partial views. Each pulse is a clue. Each change in brightness across the pulse window suggests how the beam is structured. Polarization, the orientation of the radiation's electric field, provides another clue because it can trace the projected direction of magnetic field lines as the beam sweeps by. Through such measurements, the invisible tilt becomes something that can be modelled. The misalignment between axes, born in stellar collapse, becomes measurable across thousands of light years. A neutron star with a tilted magnetic field has now reached the edge of becoming a pulsar in the observational sense. The dense remnant exists. It spins with inherited angular momentum. Its magnetic field has been amplified and organized. Its poles are offset from its rotation axis. Around it, charged particles gather, accelerate, and radiate. The geometry turns that radiation into a sweeping signal. Yet the final act still requires the beam itself to escape along the magnetic regions and pass across a distant line of sight. The tilt prepares the rhythm, but the emission must give the rhythm light. In the next movement, the focus narrows to the poles, where particles are lifted, accelerated, and guided outward, and where the neutron star begins to send its stored rotational energy into space as beams. Near the magnetic poles of a neutron star, the invisible architecture of the field becomes an open path into space. Most magnetic field lines curve outward and then return to the surface, forming closed loops that trap charged particles close to the star. But near each magnetic pole, some field lines do not close nearby. They stretch outward through the rotating magnetosphere and pass beyond the region where matter could co-rotate with the star without exceeding the speed of light. These open field lines form polar channels, narrow routes along which particles can escape. The poles are therefore not simply places on a surface, they are gateways between the compact star and the wider galaxy. In those gateways, rotation and magnetism combine to produce intense electric fields. A neutron star is an excellent conductor, and its spinning magnetic field creates enormous voltage differences across the magnetosphere. Charged particles respond immediately, electrons, positrons, and sometimes ions are pulled from the surface or formed above it, then accelerated along magnetic field lines to nearly the speed of light. This acceleration is one of the essential steps in turning a neutron star into a pulsar. The star's rotation stores energy. The magnetic field shapes that energy. The particles carry it outward in a form that can become radiation. The surface beneath the polar regions is not quiet. It is bound by crushing gravity and threaded by magnetic fields so strong that ordinary atomic behavior is altered. In some models, electrons are stripped from the surface by electric fields. In others, high-energy photons produce pairs of electrons and positrons above the surface, filling the magnetosphere with fresh plasma. These pair cascades are important because a pulsar needs charged particles to sustain its emission. A single accelerated particle can radiate a high-energy photon, and that photon, moving through the strong magnetic environment, may create a particle and antiparticle pair. Those new particles can be accelerated in turn, producing more radiation and more pairs. The result is not a simple beam made from one source, but a self-feeding plasma process, a cascade that fills the open magnetic region with moving charges. The exact details remain active areas of research, because pulsar emission involves plasma physics under conditions far beyond ordinary laboratories. Yet the broad picture remains steady. The open field lines near the magnetic poles become acceleration zones, and these zones become sources of radiation. As particles race along curved magnetic field lines, they emit curvature radiation. Light produced because a charged particle forced to follow a curved path is continually changing direction. In other regions, particles may spiral around field lines and release synchrotron radiation. They may also scatter photons to higher energies. Different mechanisms can dominate at different altitudes and in different kinds of pulsars. Radio waves may arise in coherent plasma processes, where many particles act together rather than as isolated emitters. X-rays and gamma rays may come from higher energy particles in outer parts of the magnetosphere. This is why pulsars are not all seen in the same kind of light. Some are strongest in radio waves, some are prominent in X-rays, some shine powerfully in gamma rays. The beam is not a single color or a single layer. It is a structure built from many interactions within the rotating magnetosphere. The radio beam, especially, carries a quiet mystery. Radio pulsars can be extraordinarily bright at their pulse peaks, brighter than ordinary incoherent emission would allow if every particle radiated independently. This suggests that the particles emit in a coordinated way through collective behavior in the plasma. The magnetosphere acts less like a thin spray of particles and more like a restless electrical medium, capable of organizing radiation on scales larger than individual particles. The details of this coherent emission remain one of the enduring problems in pulsar physics. The pulses are measured with remarkable precision, yet the exact microscopic process that gives radio pulsars their strength is still debated. This combination of precision and uncertainty is part of the charm of pulsars. Their timing can be understood as rotation, but their voice, the actual production of radio light, still carries unanswered questions. The beams themselves are shaped by the magnetic poles and by the altitude of emission. Close to the surface, the polar cap is small, a limited region around each magnetic pole where open field lines begin. Farther from the star, those open lines spread outward, widening the possible beam. The beam may not be filled evenly. It may have brighter patches, hollow cones, central cores, or layered components. As the neutron star rotates, a telescope does not see the whole beam at once. It cuts through the beam along a path determined by geometry. The resulting pulse profile is the brightness pattern recorded during each sweep. A narrow cut through the edge of the beam may produce a weak or simple pulse. A cut through a richer region may produce multiple peaks. If the line of sight passes near both magnetic poles during a rotation, an interpulse may appear between the main flashes. Each profile is therefore a trace of invisible structure, a moving shadow of the magnetosphere written in radio, X-ray, or gamma-ray light. At higher energies, the emission may come from regions farther out, near the outer magnetosphere or close to the light cylinder. There, magnetic field lines are stretched by rotation, and particles can be accelerated in gaps where electric fields are not fully screened by plasma. The geometry becomes more complex than a simple polar flashlight. Radiation from different altitudes can arrive at nearly the same rotational phase because of relativistic effects, including the forward beaming of fast particles and the time it takes light to travel from different parts of the magnetosphere. These effects can sharpen peaks and shift pulse shapes. A pulsar's beam is therefore not merely aimed, it is sculpted by speed, curvature, altitude, and the structure of the magnetic field. The neutron star is small, but the emitting region can extend far beyond its surface, out into a magnetosphere many times larger than the star itself. The energy budget remains rooted in rotation. Particles do not accelerate for free. The electric fields that drive them are sustained by the spinning magnetized star. As charged particles stream outward, as radiation escapes, and as a pulsar wind carries energy away, the neutron star loses rotational energy. The beam is the visible edge of a slow braking process. Every pulse is connected to an almost imperceptible lengthening of the rotation period. Over long spans, that loss changes the character of the pulsar. The magnetic field and rotation together determine how much voltage can be generated, how many particles can be accelerated, and how strong the emission can remain. When the star slows too much, the conditions needed for sustained pair production and coherent emission may weaken. The pulsar can fade from view, not because the neutron star vanishes, but because the engine no longer drives its beams strongly enough. Young pulsars often reveal the power of these beams in their surroundings. Their particle winds can inflate glowing nebulae inside supernova remnants, filling space with relativistic electrons and magnetic fields. The narrow pulses received by a telescope are only one expression of the engine. Around the star, a broader outflow may carry far more energy, carving a bubble into the debris of the explosion. In such systems, the neutron star is not only sending timed flashes into space, it is actively reshaping its local environment. The poles launch particles, the magnetosphere regulates their motion. The wind collides with surrounding gas. The remnant becomes a small but persistent power plant at the center of a fading supernova cloud. Yet the narrow beam remains the feature that gives the pulsar its name. The pulse is the meeting of emission and rotation, a lighthouse pattern produced by plasma rather than machinery. From the star's perspective, the beams stream continuously along magnetic regions. From a distant line of sight, they appear as separate flashes because the star turns. This distinction matters. A pulsar is not usually switching on and off in the way a lamp might. Its emission is directed, and the direction sweeps. The regular flicker is a consequence of geometry, not a repeated explosion. The calm precision of the signal can make the underlying process seem simple, but near the poles it is a storm of particles accelerated across enormous voltages, radiating through curved magnetic fields, creating new plasma and feeding an outward flow that drains the star's spin. The transformation from neutron star to pulsar becomes clear at this stage. The neutron star has a surface and a crust, an interior of dense matter, rapid rotation, and a tilted magnetic field. But the pulsar emerges when the open magnetic regions become active particle accelerators. Beams leave the poles because the rotating magnetosphere creates the conditions for charges to escape and radiate. Those beams carry information about the magnetic geometry, the plasma, the rotation, and the slow aging of the star. They are narrow enough to miss many worlds and strong enough, when aligned, to cross interstellar distances and arrive as a steady beat. In the darkness around the compact remnant, the poles become radiant paths. Matter falls no farther inward there. Instead, particles are lifted outward, accelerated, and turned into signal. The neutron star, once only the dense survivor of collapse, begins to speak through beams. The beams leaving a neutron star do not make a pulsar visible everywhere. They are narrow, structured, and tied to the magnetic axis, while the star itself turns around its rotation axis. From within the magnetosphere, radiation may stream outward almost continuously along open field regions. But across the galaxy, that radiation becomes a timed signal only for observers placed in the path of the sweep. This is the lighthouse effect, the simple geometric principle that makes a pulsar appear to flicker with such astonishing regularity. The neutron star is not swelling and shrinking. It is not exploding again and again. It is turning. Its beams pass through space, and when one crosses Earth, telescopes receive a pulse. Then the beam moves away, the signal fades, and the star continues its rotation until the geometry repeats. What appears as a flashing point is the intersection of a rotating beam with a distant line of sight. The calmness of the pattern hides the violence of the machine that produces it. Beneath each pulse lies a dense remnant, a magnetic field strong enough to organize plasma and particles moving through curved field lines at nearly the speed of light. Yet the timing itself can be understood through rotation. A pulsar is a clock whose hand is made of radiation. Each sweep marks one turn of the star, or one encounter with a magnetic pole, depending on the viewing geometry. If only one beam crosses the line of sight, one pulse appears during each rotation. If both magnetic poles become visible, two pulses may appear, often separated by a phase that reveals the star's orientation. The received signal is not the whole magnetosphere, but a repeating slice through it. Every rotation offers nearly the same slice again, so the pulse profile can remain stable, a recognizable shape repeated over years. This stability was one reason pulsars were so surprising when first discovered. The sky contained variable stars, flares, eclipses, and bursts, but these radio signals arrived with a precision that seemed almost artificial before their natural origin became clear. The explanation was not an engineered beacon, but a stellar remnant spinning with remarkable steadiness. The lighthouse effect also explains why detection is selective. A neutron star may be active, radiating strongly along its magnetic beams, yet remain invisible as a pulsar from Earth if the beams never sweep this way. The observed population is therefore only a partial map of the true population. For every pulsar detected, there may be many neutron stars whose beams point elsewhere, or whose beams once crossed the line of sight but no longer do because of slow changes in orientation, emission strength, or spin. The galaxy is not filled only with the pulsars that telescopes record. It is filled with compact remnants, many silent from this particular viewpoint. The pulse is a matter of chance as well as physics. A star must be born with sufficient rotation and magnetic activity, and its beam must find the observer. In that sense, each detected pulsar is an alignment event spread across interstellar distance. The beam may have travelled for hundreds or thousands of years before arriving, crossing dust, gas, magnetic fields, and the thin plasma between stars. By the time it reaches a radio telescope, it is faint, stretched by dispersion, and altered by the material it passed through. Yet its rhythm remains. Interstellar plasma delays lower frequency radio waves more than higher frequency waves, spreading the pulse slightly in time. Astronomers can measure this delay and infer how many free electrons lie along the path. Thus, even the distortion of the lighthouse beam becomes useful. Pulsars illuminate not only themselves, but also the space between stars. Their regular flashes make the galaxy measurable in a different way, turning the interstellar medium into a medium through which timing can be read. The shape of a pulse carries additional information. Some pulsars show narrow peaks, suggesting a sharp crossing through a bright emission region. Others show broad profiles, multiple components, or subtle drifting patterns. These features reflect the structure of the beam and the physics of the magnetosphere. A pulse profile can be imagined as a cut through a rotating cone or fan of emission, but the real structure is more layered than a simple cone. Different radio frequencies may come from different heights above the magnetic pole. Higher energy radiation may originate farther out, closer to the outer magnetosphere. The same neutron star can therefore present different pulse shapes in radio waves, X-rays, and gamma rays. Each wavelength samples a different part of the rotating engine. When these signals are aligned and compared, they help reconstruct the three-dimensional geometry that no telescope can image directly. The lighthouse effect is simple in outline, but rich in detail. It turns an unseen magnetic structure into a time series, and from that time series astronomers infer angles, heights, plasma behavior, and the energy loss of the star. The regularity of the pulses allows extraordinary measurements. Once a pulsar's period is known, each arriving pulse can be predicted. If a pulse comes slightly early or late, the difference may reveal something physical. The pulsar may be slowing down as it loses rotational energy. It may be moving through space, causing the arrival times to shift. It may orbit another star, producing regular delays as the pulsar moves closer to and farther from Earth during its orbit. It may experience glitches, sudden internal adjustments that briefly change its spin. In some cases, timing can reveal planets orbiting the pulsar, because their gravity tugs the neutron star and changes the arrival times of the pulses. The lighthouse, once recognized, becomes a measuring instrument. Its beam marks rotation, and rotation marks motion, gravity, and the hidden interior. A pulse is therefore both a signal and a ruler. It is a brief flash, but it can carry the signature of an orbit, a slowdown, a starquake, or the passage of gravitational waves through space. The precision depends on the neutron star's compactness. A larger, more diffuse star could not keep such exact rotational time, while also producing a narrow beam. A neutron star is small, massive, and strongly bound. Its surface and magnetic field rotate as a coherent system, and its moment of inertia changes only slowly except during glitches or interactions. This makes the lighthouse effect far more precise than a casual sweep of light. The rotating beam is anchored to an object whose physical scale is tiny compared with the distances it signals across. and whose gravitational binding helps preserve its stability. Still, the pulse is never perfectly eternal. The star spends energy with each rotation. The magnetosphere exports particles and electromagnetic radiation. The spin period gradually lengthens. The lighthouse slows. For many pulsars, this slowdown can be measured as a tiny change in the interval between pulses. From that change, astronomers estimate the rate of energy loss, the strength of the magnetic field, and an approximate characteristic age. These estimates are not perfect clocks for the star's true age, because birth period and magnetic evolution complicate the picture, but they help place pulsars into broad stages of life. Young pulsars are often energetic, bright in high-energy radiation, and sometimes embedded in glowing nebulae. Older pulsars tend to spin more slowly and may weaken until their beams no longer remain active. The lighthouse effect has a beginning and an end, even if the neutron star itself persists. There is also a softer consequence of the lighthouse geometry. It means that the universe can contain powerful signals that are real but unseen. A beam can pass just beyond the planet, missing all instruments by a small angle. Another can cross Earth only during a certain era, before slow precession or alignment changes carry it away. Detection is never the same as existence. Pulsars remind astronomy that the observable sky is filtered by direction, sensitivity, timing, and patience. The night is not silent because nothing is speaking. It is silent in places because the beams are aimed elsewhere, because the signals are too weak, or because the rhythm has not yet been noticed. When a pulsar is found, it is a rare meeting between an ancient stellar remnant and a line of sight drawn across the galaxy. The beam left the neutron star long ago, swept outward from its magnetic pole, travelled through interstellar space, and arrived at a small world at the right moment in the star's rotation. The telescope records a pulse, then another, then another. With each arrival, the dense remnant announces not a message in words, but a physical fact it is turning. It is magnetic, and its geometry includes the Earth. This is the moment when a neutron star becomes a pulsar to an observer. The object may have possessed all the necessary machinery before, but the name pulsar belongs to the observed rhythm. It is the neutron star made visible through repetition, the compact remnant translated into time. In the lighthouse effect, density becomes timing, magnetism becomes direction, and rotation becomes a pulse. The star itself remains distant and almost unimaginably small, but its sweep reaches across space with enough order that a hidden stellar corpse can be known by the beat of its beams. Pulsars are first recognized by rhythm, but their rhythms do not all move at the same pace. Once a neutron star is seen as a repeating signal, astronomers begin to measure the pattern with care. They record the spin period, the time between one pulse and the next. They measure how that period changes, often by an amount so small that it becomes meaningful only after many observations are gathered. They compare the pulse at radio wavelengths with signals in X-rays or gamma rays. They ask whether the pulsar is alone or moving around a companion. From these measurements, a population begins to appear, not a single kind of object, but a family of rotating neutron stars at different ages, with different magnetic fields, different histories, and different ways of spending their stored energy. The first broad division is between ordinary pulsars and the extremely fast millisecond pulsars. Ordinary young pulsars may rotate in fractions of a second or in several seconds, and they usually slow down steadily as their magnetic fields and particle winds remove rotational energy. Their pulse periods lengthen with time. This slowdown is tiny from one rotation to the next, but it is persistent, like a clock whose hand is being drawn through a trace of resistance. By measuring both the period and the rate of slowdown, astronomers can estimate how quickly the pulsar is losing energy. They can infer a characteristic age, a rough magnetic field strength, and a spin-down power, the rate at which rotational energy is being carried away. These estimates are not perfect biographies. A neutron star may have been born spinning faster or slower than assumed. Its magnetic field may evolve. Its environment may affect its motion. Yet the pattern is useful. A pulsar that spins quickly and slows rapidly is usually young and energetic. A pulsar that spins more slowly and loses energy more gently may be older, quieter, and closer to the fading edge of the radio pulsar population. On a diagram of spin period against slowdown, pulsars spread into recognizable regions. Young energetic pulsars occupy one part of the landscape, often with strong magnetic fields and bright high-energy emission. Older ordinary pulsars drift toward longer periods and weaker activity. Some may eventually cross what is called a death line, a boundary in this diagram where the voltage in the magnetosphere may no longer be able to sustain the particle cascades needed for strong radio emission. The term is dramatic, but the physical idea is calm. The neutron star does not die again. It simply becomes harder for the rotating magnetic engine to produce a detectable beam. The remnant remains, cooling and spinning in space, but its lighthouse may grow faint. This gradual fading helps explain why neutron stars can outnumber the pulsars currently known. The pulsar phase is a visible chapter, not the whole life of the compact object. Millisecond pulsars tell a different story. They spin hundreds of times each second, with periods measured in thousandths of a second, and their rotation can be astonishingly stable. Many of them are found in binary systems, and their speed is thought to come from recycling. An old neutron star, once slowed by age, can orbit a companion and draw matter from it. As gas spirals inward through an accretion disk, it carries angular momentum. Some of that angular momentum is delivered to the neutron star, spinning it up again. The result is an ancient remnant made fast by long contact with another star. When the accretion later weakens or stops, the neutron star can emerge as a millisecond radio pulsar. It is old in years, but youthful in spin. These recycled pulsars are among the most precise natural clocks known, because their magnetic fields are often weaker than those of young pulsars, and their spin down can be very slow. Their steadiness makes them powerful tools for timing experiments across the galaxy. Binary companions add another layer of classification. Some pulsars orbit white dwarfs, the compact remnants of smaller stars. Some orbit other neutron stars. Some are found in systems where the pulsar wind is eroding a low-mass companion, gradually stripping it away. The orbital motion changes the arrival times of pulses. When the pulsar moves closer to Earth in its orbit, pulses arrive slightly earlier. When it moves farther away, they arrive later. These shifts allow astronomers to map the orbit with remarkable precision. In certain systems, the timing reveals relativistic effects, such as the slow rotation of the orbit itself, gravitational time delay as pulses pass near a companion, and the gradual shrinkage of the orbit as gravitational waves carry energy away. A pulsar in a binary system therefore becomes more than a clock. It becomes a probe of gravity, using its pulses as tick marks moving through curved space-time. The kind of light pulsar emits also shapes its identity. Many pulsars were first discovered in radio waves, where their beams can be measured as sharp, repeating flashes. Radio emission often comes from regions above the magnetic poles, though the exact mechanism remains a deep question. Some pulsars are also strong X-ray sources, especially young ones with hot surfaces, active magnetospheres, or surrounding pulsar wind nebulae. Gamma-ray pulsars reveal some of the most energetic particle acceleration in the magnetosphere, often from regions farther out than the traditional radio beam. A pulsar may appear differently depending on the wavelength used to observe it. In radio light, one part of the magnetosphere may speak clearly. In gamma rays, another part may dominate. Some pulsars are nearly invisible in radio waves but bright in gamma rays. Others are radio strong and high-energy faint. These differences do not require separate kinds of stars in every case. They may reflect viewing geometry, magnetic field structure, age, and whether radiation is produced. Magnetas form a related but distinct group of neutron stars. Their magnetic fields are exceptionally intense, and their observed activity is often powered more by magnetic energy than by rotation alone. They can emit bursts and flares in X-rays and gamma rays, sometimes irregularly, as magnetic stresses shift the crust or reconfigure the magnetosphere. Some magnetaires have also shown radio pulses for limited periods, blurring the boundary between categories. This reminds astronomers that classification is a way of organizing behavior, not a set of walls placed by nature. Neutron stars can change. A source may quiet down or brighten, a pulsar can glitch, a magnetar can enter an active phase. A binary system can switch between accretion-powered X-ray emission and rotation-powered radio pulsations. The family is connected by the same compact foundation, but the outward expressions can vary with time. Glitches add another signature to pulsar timing. In some pulsars, the rotation suddenly speeds up by a tiny amount, then relaxes toward its earlier slowdown. These events are especially common in young pulsars and are thought to involve the crust and interior superfluid exchanging angular momentum. Timing noise, slower and less regular wander in the pulse arrival times, can also appear, reflecting magnetospheric changes or internal processes. Even the best cosmic clocks have textures in their ticking. For ordinary timing, these irregularities are complications. For physics, they are gifts. They allow the unseen interior to leave traces in the observable rhythm. A perfect clock would tell time but reveal little about its mechanism. A pulsar is precise enough to be useful and imperfect enough to be informative across the whole population. Pulsars become a map of neutron star evolution. A massive star collapses and leaves a young, hot, rapidly rotating remnant. If its magnetic beam crosses Earth, it appears as a young pulsar, perhaps powering a bright nebula. As it loses energy, it slows and fades. If it remains alone, its beam may eventually weaken beyond detection. If it lives in a binary system, it may later accrete matter and be spun up into a millisecond pulsar. If its magnetic field is unusually strong, it may behave as a magnetar. If its beam points elsewhere, it may never be recognized as a pulsar from Earth at all. These paths are not rigid tracks, but they give order to the many signals observed in the sky. Each pulse period, each slowdown rate, each wavelength, and each companion helps place the object within a longer life. Time is written in pulses, but not only the time of one rotation. The pulses carry the history of birth, aging, companionship, magnetic decay, and hidden interior motion. When astronomers listen to a pulsar, they are not hearing a single note repeated without meaning. They are measuring a compact star as it spends energy, interacts with its surroundings, and moves through its evolutionary path. Some beats are young and forceful. Some are ancient and exquisitely steady. Some are disturbed by glitches. Some are bent by binary orbits. Some shine in radio waves. Others in X-rays or gamma rays. Together they form a population of cosmic clocks, scattered across the galaxy, each one made from the collapsed heart of a massive star, and each one revealing a different way for a neutron star to become visible through rhythm. The value of a pulsar does not end with the explanation of how it forms. Once the neutron star is born, once its magnetic field is tilted, once beams leave the poles and sweep across a fortunate line of sight, the object becomes more than a stellar remnant. It becomes a laboratory placed far beyond any human instrument, testing matter and gravity in regimes that cannot be built on Earth. A pulsar is small enough to seem like a point in a telescope, yet its regular pulses allow it to be measured with a delicacy that would be impossible for many larger and brighter objects. Each flash carries timing information. Each slight delay, advance, drift, or distortion can reveal a physical process. In this way, the pulse becomes a messenger from extremes. It comes from a place where matter has been compressed beyond atomic form, where magnetic fields guide particles at nearly light speed, where space-time is curved strongly by the mass of a star contained inside a city-sized sphere. The first great use of pulsars is as clocks. Their rotation can be so stable that the arrival times of pulses can be predicted across long spans, and this stability turns them into tools for measuring motion and gravity. A solitary pulsar reveals its own slowdown, showing how rotational energy is being drained into radiation and particle winds. A pulsar in a binary system reveals much more. As it orbits another star, its pulses arrive early and late in a repeating pattern, tracing the orbit with extraordinary precision. If the companion is another compact object, the system may become a testing ground for general relativity. The orbit can slowly shift. The pulses can be delayed as they pass through the curved space-time near the companion. The system can lose orbital energy through gravitational waves, causing the orbit to shrink in a way predicted by relativity. Long before gravitational waves were directly detected on Earth, binary pulsars provided indirect evidence that such waves carry energy away from orbiting masses. A rotating neutron star, timed patiently from a distant planet, became proof that space-time itself can ripple and drain motion from a system. Pulsars also help reveal the nature of dense matter. Their masses, radii, cooling rates, glitches, and spin behavior all carry clues about the interior. The existence of very massive neutron stars places strong constraints on the equation of state, the relationship between pressure and density inside the remnant. If dense matter were too soft, it could not support such weight against collapse. If it is stiff enough, neutron stars can survive at higher masses. Every precise mass measurement narrows the possibilities. Pulsar glitches add another kind of evidence. When a spinning neutron star suddenly changes its rotation rate by a tiny amount, the event suggests that angular momentum has shifted between the crust and the superfluid interior. The pulse timing becomes a seismograph for a star that cannot be touched. It records small internal rearrangements from thousands of light-years away. The crust, the superfluid vortices, the magnetic stresses, and the unknown core all leave faint signatures in the rhythm. Pulsars are also probes of the space between stars. Radio pulses travel through interstellar plasma, and that plasma delays lower frequencies more than higher frequencies. By measuring the dispersion of the pulse, astronomers infer the number of free electrons along the path. Many pulsars in many directions help map the ionized gas of the galaxy. Their signals can be scattered, broadened, or polarized by magnetic fields and turbulent plasma. These distortions may seem like obstacles, but they become information. The beam that leaves a neutron star arrives carrying not only the identity of the pulsar, but also the imprint of the medium it crossed. The galaxy becomes partly readable through the way it alters the pulse. Some pulsars serve as markers for navigation, because their periods and positions can be known with great precision. They have been considered as natural beacons for spacecraft travelling far from Earth. A spacecraft able to detect selected pulsars could compare the observed pulse arrival times with predicted patterns and estimate its own position. Much as navigation on Earth can use timed signals from satellites, in this case, the satellites are collapsed stars, scattered through the galaxy, each one keeping its own ancient rhythm. The idea gives pulsars a practical dimension without reducing their mystery. They are both cosmic relics and possible guideposts, clocks born from catastrophe that may help travellers orient themselves in deep space. Pulsars have also opened unexpected windows onto planets. The first confirmed planets beyond the solar system were found not around a sun-like star, but around a pulsar. Their presence was revealed by tiny shifts in pulsar arrival times, caused by the gravitational tug of orbiting bodies. This discovery was surprising because a supernova seems like an unlikely place for planets to survive or form. Yet the timing was clear. Around a stellar corpse, worlds existed. They may have formed from debris after the explosion, or survived in altered orbits through a more complicated history. Either way, pulsar planets show that planetary systems can arise in environments far stranger than the gentle disks around young stars. The same method also demonstrates the sensitivity of pulsar timing. A compact star flashing across the galaxy can reveal bodies far smaller than stars by the slight wobble they impose on its motion. At the largest scales, collections of millisecond pulsars become instruments for detecting gravitational waves with wavelengths far longer than those measured by ground-based detectors. A pulsar timing array watches many stable pulsars across the sky. If a long gravitational wave passes between Earth and those pulsars, it can subtly stretch and compress space-time, changing the arrival times of pulses in a correlated pattern. The effect is extremely small, requiring many pulsars and many years of observation, but the principle is profound. The galaxy itself becomes a detector, with Earth at one end and a network of neutron star clocks at the other. Such waves may come from pairs of supermassive black holes orbiting in distant galaxies, from the slow background murmur of cosmic structure, or perhaps from more speculative sources in the early universe. Here again, pulsars turn repetition into reach. Their steady beats make it possible to listen for motions far beyond the scale of individual stars. Some ideas push even farther into uncertainty. Pulsars may help test models of dark matter if compact clumps or exotic particles influence their timing, their heating, or their surrounding environments. They may help constrain the existence of primordial black holes if such objects pass near pulsars or affect their signals. These possibilities remain speculative, but they show the range of questions that pulsars touch. A pulsar begins as a collapsed core, yet its usefulness spreads outward into nuclear physics, plasma physics, relativity, galactic structure, planetary science, navigation, and cosmology. It is a small object with a large scientific shadow. The reason is the combination of extremity and regularity. Many cosmic events are extreme but chaotic. Many clocks are regular but ordinary. Pulsars are both extreme and regular, and that combination makes them rare instruments of discovery. The transformation from neutron star to pulsar is therefore not just a change in visibility, it is the creation of a signal that can be used. A neutron star alone is already one of the universe's most remarkable objects, but a pulsar is a neutron star whose rotation, magnetism, and geometry have made its existence measurable in time. Its pulses cross interstellar distances and arrive as ordered flashes. From those flashes, astronomers infer the collapse of massive stars, the behavior of dense matter, the curvature of space-time, the distribution of plasma in the galaxy, and the presence of unseen companions. The beam is narrow, but the knowledge it carries is broad. The story that began with a massive star losing its balance ends with a remnant that gives balance to measurements across space. Gravity destroyed the original star, but from that destruction came one of the most precise natural clocks known. The pulsar is not alive, and yet it ages. It is not a machine, and yet it keeps time. It is not a lighthouse built with purpose, and yet its beams sweep the darkness with a rhythm that can be read. Somewhere in the galaxy, a neutron star turns. Its magnetic poles send radiation into space. Most of that radiation misses most worlds. But when the beam crosses Earth, the remnant becomes present through repetition. A pulse arrives. The star turns. Another arrives. In that quiet sequence, the universe offers a record of collapse, density, magnetism, motion, and time itself, all carried by the fading spin of a dead star that has become a cosmic laboratory. In the long quiet after the pulses fade from the mind, the neutron star remains where the story has left it, turning in the dark with a patience that belongs to no living thing. Around it, the scattered remains of its parent star continue to drift outward, becoming thinner, colder, and more mixed with the wider galaxy. The old furnace is gone, but not erased. Its matter has entered space again, and its core has become a small, dense clock, keeping time by losing time, giving away the motion that collapse once compressed into it. Each beam that leaves its magnetic poles is brief compared with the age of stars, yet each one carries the memory of the same deep sequence balance: exhaustion, collapse, explosion, remnant, rotation, field, and light. A pulsar is not a final answer to the mysteries of neutron stars. It is a doorway into them. Beneath a signal, matter may flow without friction. Magnetic fields may thread hidden superconducting regions, and particles may crowd so closely that the inner language of nuclei begins to change. Above the surface, charged particles rise along invisible paths and turn the star's spin into radiation. Far away, a telescope receives only the passing rhythm, a narrow sweep from a body too small to see directly and too extreme to compare with ordinary worlds. The pulse arrives, vanishes, and returns. In that repetition, the universe becomes briefly measurable. Gravity is heard as timing. Magnetism is seen as direction. The death of a massive star becomes a steady mark across interstellar space, and as the remnant slowly turns down its ancient energy, it leaves behind a softer thought even in collapse. The cosmos can make order, even from destruction. It can make a clock, even from the heart of a dead star. It can send a calm and regular signal through the dark,